Hey all, in this lesson we are going to start talking about 3D shapes. So not just the flat shapes that we've been looking at all year, thinking about shapes that have height, length, and width. And we're going to be talking specifically about two measurements that we can take from those shapes. We're going to be talking about the volume. The volume, that's like how much we can fill the shape with. And then the surface area, that's kind of like if you were trying to wrap the shape with wrapping paper, how much wrapping paper would you need to cover that shape, to cover the whole surface? And so we're going to calculate those specifically in a future lesson, but for right now we're going to talk about the relationships between those. And so when we have two 3D figures that are similar, much like when we talked about similar triangles, they're going to have a scale factor between them where every dimension from one shape that matches the dimension in another shape, they're going to have the same scale factor. They're all going to be in proportion. And that would be for lengths, widths, heights. We'll look at some that'll have a radius. Using that scale factor, we can figure out what the ratio of their surface areas would be, because if they're similar figures, they're going to have a relationship between the surface areas. So we can take that scale factor and we can square it to find out what the ratio of the surface areas would be. And then we can take that one more step and find the ratio of volumes. Notice we have the letters A and B. There's no real reason we choose A and B. A can be the smaller shape, A can be the bigger shape. Typically, I'm going to write the smaller shape on top, but we can use that scale factor to find the ratio of surface areas. We can use that scale factor to find the ratio of volumes, and then we can interchange between the three of them if we need to, and I will say more on that in an example. So here we can actually see some three-dimensional shapes. So in this first example, I have two rectangular prisms. The rectangular prisms, you can see in each of these shapes, we have a height of the prism. We have, we'll call it length, and then we have a width. And so if these are similar prisms, then the two green pieces should have the same fraction as the same red pieces as the blue pieces. And I'm going to do mine as the small on top and the big on the bottom. You could do it the other way around if you want to. Neither is more correct. I just like to put the small number on top because I think that it's more aesthetically pleasing to our eyes to see a fraction that has a smaller number on top. And so I can choose any of the dimensions I want to, the green height, the red length, or the blue width. And we can write a scale factor. So I chose those green heights, 12 over 40. And then we can always reduce, we should always reduce our fractions, or at least try to, and that would reduce to a scale factor of 3 over 10. If we chose the red pieces, if we would have chosen 24 over 80, that should reduce to the same fraction, 3 over 10. 18 over 60 should also reduce to the same fraction, 3 over 10. And so if in a future lesson, we will actually calculate the surface area of these shapes, the volume of these shapes, but what we can figure out right now is what would the ratio of the volume of the small rectangular prism be to the big rectangular prism, and we are going to do that by squaring A and B. So A is 3, B is 10. And so if we square both of those, we will get the ratio of surface areas. So our surface areas will have a ratio of 9 to 100. We can do the same thing for volumes. Okay, remember surface area is how much area we can cover on the surface with wrapping paper. The volume would be like how much water could we fill these shapes up with. If we use our A and B and we cube them, we put them to the third power, that's 3 times 3 times 3, 10 times 10 times 10. we get the ratio of the volume. So you can see that the bigger prism holds a lot more volume. The bigger prism also requires a lot more wrapping paper to cover the surface. And we could do the same thing with these two pyramids. These are pyramids. These are hexagonal pyramids. You can see they have this height right here. Those two should match. And you can see that the sides of the base of the pyramids, remember those little lines mean they're all the same. So this side that's 18 should have the same fraction with this side that's 54 as we'd have with the purple ones. And so we can find their scale factor. I use the purple heights, 27/81, which reduced to 1/3. You can go into Desmos, you can put 27 divided by 81, then you can click that little fraction button and it should reduce it to 1/3. And then if we take that 1/3 and we square both of them, we're going to get the ratio of surface areas is 1/9. So the bigger hexagonal pyramid has a surface area that's 9 times that of the smaller one. And then if we cube those, we're going to get a 1 on top again, because 1 to any power is 1. And you can see that the bigger pyramid has 27 times the volume. It holds 27 times the amount of water as the smaller one. So now we can take those ideas and we can sort of go from one to the other. So we started with regular dimensions and we could write a scale factor and then find a ratio of surface areas and a ratio of volumes. In this example, by the way, I changed those numbers just to make the calculations a little nicer for our first time around. So change those to 9 pi and 25 pi. We have the surface areas of these two cylinders. And so I can find the ratio of surface areas by writing a fraction, just like we did with the scale factor. And I'm going to do the smaller cylinder on top. So I'm going to go 9 pi over 25 pi. And the pi's will cancel, and I'm left with a ratio of 9/25. And we should always check that in Desmos. That doesn't reduce to a simpler fraction, so that's our ratio of surface areas. So now we have a squared and b squared, not to be confused with Pythagorean theorem. So the way that we got rid of a square when we were dealing with problems with Pythagorean theorem is that we would square root. And so if we want to find a and b, we can take that 9/25 and we can square root it, and it will give us the scale factor. So the measure or the ratio of dimensions. So in cylinders, we will have heights and we will have radii. And so those are dimensions that should be in a scale factor. So if we square root the whole thing, we can then individually square root 9. The square root of 9 is 3. The square root of 5 is 25. The square root of 25 is 5. And so we get our scale factor of 3/5, which we can then go to use and find the ratio of volumes by doing what we did before and just putting those two numbers to the third power. So 3 to the third power, 5 to the third power gives us 27/125. So this is just a way, or I'm just trying to show you a way where if we know one ratio, we can find the other ones. If I know the ratio of volumes, I can also find the ratio of surface areas and the ratio or the scale factors. So down here, I have volumes. And again, I changed them just so that our calculations would be kind of nice on our first examples. This time, the bigger one is on the left of these rectangular pyramids. If you notice, I'm naming these things by the shape of the bottom. That's a rectangle, it's a pyramid, it's a rectangular pyramid. So I can write the ratio of volumes by doing 64/1,331. If I put that in a Desmos, it won't simplify to a nicer fraction. There's my ratio of volumes. That's my A cubed and B cubed. In order to undo a third power exponent, we do the cube root, kind of like the square root. And so if I want to find A and B, I could do this straight into Desmos, the cube root of A cubed over B cubed. And I can get 4 over 11. So any dimensions in my pyramid, let's say that side and that side, if I write the small over the big, that fraction should reduce to 4 over 11. And now that I have A and B, I can go find the ratio of surface areas by squaring A and B. 4 squared, 11 squared gives me 16 over 121. This is sort of the final mashup of how I can use information. Here I don't know what the shapes are, but I know that the scale factor is 1 over 2, so that's my A and B. I know that I have 1 surface area and 1 volume, and I believe that is from the smaller shape, the smaller of the 2 shapes. And so I can use all this information to find the surface area of the other shape and the volume of the other shape just by knowing what the scale factor is, by understanding how to get the ratio of surface areas and volumes. And I don't even need to know what shapes these are. So if I want to find the surface area, I'm first going to take that A over B, 1 over 2, and I'm going to square those to get a ratio of surface areas to be 1 to 4. And then I can set up a proportion much like we did with similar triangles, like we did in the last unit when we had arc length and sector area that we were solving for. If I have the surface area of my smaller shape and I divide it by the surface area of my larger shape, it should reduce to a fraction of 1 over 4. That's what that ratio of surface areas tells me. I can cross multiply. I do 1 times the surface area. That leaves me with just the surface area. 90 times 4. And that gives me the surface area of the bigger shape is 360 yards squared. I can do the same thing for volumes. I can take that A over B, 1 over 2, and I could raise them both to the 3rd power. So I'm raising them to the 3rd power to get a ratio of volumes of 1 over 8. And so my volume of my smaller shape was 216. If I divide it by the volume of my larger shape, those two should reduce to 1 over 8. Again, I can cross multiply. 1 times the volume gives me just the volume. 8 times 216 over here gives me 1,728 yards cubed. So this is an application of how we can use those ratios and one dimension from one shape to find the dimension in the other shape. Remember, if you have any questions about this, please make sure that you ask. Make sure you're doing the practice and you show us the practice so that you get credit. But as always, make sure you take your time, and good luck.